My name is Alex Smith. I am in 5th grade and I go to the San Lorenzo Valley Charter School in Ben Lomond. And this is my project called My Mini Model Mass Driver. And here it is right here. So, this is what they might look like on other planets or the moon, like Mars or the moon. This is from NASA. This picture is from actual NASA. And it was made in 1977. This one, right there, was made from an artist in 2018 of what they also might look like. And here are some mass driver facts. Escape, escape velocity is like the speed that something has to go to break free of the pull of gravity on that so-called moon or planet. And the escape velocity for Earth is 11.2 kilometers a second, which is really fast. The escape velocity for the moon is 2.38 kilometers a second, which is still really, really fast, but it's not as fast, but it's still really fast. And for a mass driver to be safe for humans, it has to be over 1,000 kilometers long because it has to accelerate gradually and not like just immediate jump into space. Because otherwise you just like immediately die. You'd be like pushed. And even on the moon it'd have to be really long. So now assembly. These are pictures of me building it. That little pen I'm using is a soldering iron. And that little coil of metal is called solder. A soldering iron is like a 800-degree pen, an 800-degree 3D pen that you can use to you can use to glue stuff together, but with molten metal. And it's really cool, but really, really dangerous. And here's some more pictures of me doing it. And here's the part list that I used. These are all the parts that I used. Here's the washer, right there, those little circles. The infrared LED and photodiode. The photodiode is right here, and the LED is on the other side. And I used MOSFETs. These MOSFETs were not powerful enough at all. For them, it can do 110 amps, like continuously, but only like maybe 390 for like a tiny pulse. And for the bigger MOSFETs, the bigger, beefier ones, these big black squares, those can do 400 amps continuously and around 900 amps for a little tiny pulse, which is a lot. That's a lot. That's like a lot. And there's also the resistors, 10K, 1K, and 220 ohms. And here's the little steel payload. Here's a little section of two bells right there. Here's the wire that we used. 18 mag watt. I forgot. 18 gauge mag wire, which means 18 gauge is like the size of it, the thickness of the wire. And here are the LEDs, the little red LEDs that are right there, there. And a diode, a 20 amp diode. The diode is like a one-way switch. Like, stuff can Energy can go through one way, but not the other. And a MOSFET is like a giant, really powerful switch where you there are three parts to it: gate, drain, and source. The source is where all the electricity goes in. The gate holds it all back, and then when it's activated, it lets it all out through the drain. So like a really powerful, tiny technological dam. And like the electricity is water. And then this is the actual mass driver mass driver model that I built. And all three of these coils are lined up to launch a projectile really fast. So when I did this, we used the 18 gauge wire and we wrapped it around right there. And when power is applied to that coil of wire, it creates a magnetic force. And when that magnetic force is created, you put in a little projectile like that, and it flies through. But you can't just leave the power on, otherwise it'll get sucked back into the middle and stay on. So you have to turn it off at the perfect time to have it continue going. And that's what we've done with these three coils lined up. It just like hits one, goes really fast, hits the other, goes even faster, hits the last one, goes even faster. And that works by when the front of the payload hits the sensor and it's kind of like a laser. When it breaks the laser, it tells the battery, hey, you need to send power. It also turns on this LED. And when that happens, it creates a magnetic field, and when the back of the payload gets out of the laser, it turns it back on, the LED is off, the battery stops producing power, the magnetic field is gone, and it keeps going. And if you do that 3 times in a row, it goes really fast. And then that's what we have here in the table of data. Coil 1. All of these numbers right here is how many frames is, this is 30 centimeters apart, and how many, on a 240 frame per second slow-mo camera, there is like, on coil 1, there's like around, the average is 14.67 frames to go from this point A to point B. With coil 2, it's around 13.67, which is a little bit faster, but not that much. And coil 3 is 16.3. 16.333, which is a lot slower than all of the others. And I'll explain that in a second. But coil 1 and 2, and the lower this number is, the lower this is, and the higher, the faster it's actually going. So coil 1 and 2 is around 11.67, and coil 1, 2, and 3 altogether is around 11.333. And all of that, the 1, 2, and 3, is at 6.3 meters per second, which is really fast. And a meter is like this big, like times 6 that per second. And a little bit more. That is really, 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 really fast. And about coil info, we used 18 gauge wire, 80 total turns. Turns are like how many windings it is around the tube. And a 12 volt battery. And for just coil 3 properties, 10 turns per winding, 4.6 meters of wire for the entire coil, and 125 amps. That is 1,500 watts, which is a lot. Like, a lot. Because, like, that is 1.5 kilowatts. The generator we have outside is 4 kilowatts, and it's a really big, bulky, super generator. And the estimated coil properties for just 1 and 2 is 20 turns per winding, which is doubled in 10, 3.5 meters of wire, which is a lot less, 165 amps, all of that together in this program called utmel.com/tools and / a bunch of stuff. 1980 watts. That is practically 2 kilowatts. That is so much power going through just these tiny little coils of wire. That is insane. And that's why I have the sticker. Science is like magic, but real, because science is like magic, but real. It is so powerful, so cool, so dangerous, so much. And I really hope you like this, because I put a lot of effort into it, and it was really fun to make, and we did a lot of stuff, and I really hope you liked it. I think that is it.